Okay, so Sergey, your slides are up. I'm just waiting for a thumbs up here.
Shall I start?
Are we okay to go? Yeah, okay. Okay, first up we have Sergey Popov. And Sergey, you have 20 minutes for this. I'll give you a nod with 5 minutes to go. So,
okay, perfect. Thank you.
Okay.
Good morning. I'm very glad to present this talk about emission mechanisms for FRBs and their relation to observations. So let me start from brief presentation. Where do we stand now? If we believe that the majority of FRBs are due to a single type of sources, then we are more or less sure that FRBs are due to strongly magnetized neutron stars. Of course, the population of FRBs can be defined not by a single type of sources. And if you didn't see yet, I recommend to look, for example, at the e-talk by Mariano on a possible candidate for neutron star coalescence, which produced a fast radio burst. But still, the discovery of a fast radio burst coincident with a high energy burst from a galactic magnetar, and on the left, you see a picture from the paper by Ridne and collaborators. This discovery really demonstrates that magnetars can produce FRBs, and if we're dealing with a population dominated by a single type of sources, then they might be strongly magnetized neutron stars. Then we believe that the magnetic energy is released, and finally, actually, it was the first obvious thing about the emission mechanism. It's necessary to have a coherent emission mechanism. So any proposed mechanism might explain the following characteristics. Of course, the list is not complete, but it's necessary to explain the range of luminosities, duration of the bursts, variety of morphological types, rapid variations, huge brightness temperature, repetitions for some of the sources, high level of polarization, complicated behavior of polarization in the case of repeaters, relatively narrow spectra in radio, and different types of frequency drift, which is not limited to the set trombone effect only. At the moment, we have two major frameworks in which people try to develop a model of the emission mechanism, and this situation was nicely reviewed by Bing Zhang a year and a half ago in the Nature paper. And I would say that generally things did not change dramatically since that review was published. So either the emission mechanism is related to some magnetospheric processes, or it's related to relativistic shocks. And so the second mechanism is operating at relatively large distances, like 10 to 14 centimeters from the neutron star. So the external shock framework was initially proposed in the paper by Yuri Lubarsky in 2014. The idea is based on studies by Arons and his co-authors. The idea is that high-frequency synchrotron maser can operate in the case of relativistic magnetized shocks, and magnetars can provide a scene for this mechanism after a magnetar burst. It can be a giant flare or a weaker flare or a hyperflare. A pulse is propagating, and then it starts to interact with the media surrounding the neutron star. And this mechanism can explain main characteristics of fast radio bursts. And since 2014, many models have been proposed, and I'll briefly speak about some of them. What is important, it's possible to explain the energetics, the duration of typical, I would say, fast radio bursts, and typical frequencies around several gigahertz. So these equations are taken from a recent review by Lubarsky published in Universe last year. So many modifications of this scenario have been proposed, and different researchers continue to develop this field. So on the left, there is a plot from a paper by Andrei Beloborodov. In this model, a burst is produced due to a blast wave, which originated due to a magnetar burst. So blast is propagating and it starts to interact with the surrounding medium. And the medium around the magnetar can have a quite complicated nature. Also, a burst can interact with the tail of the previous burst. This might be typical in the case of repeaters. So this model can explain relatively higher repetition observed in some sources. And more or less, this picture looks somehow one-dimensional. So we are on the line of sight, and everything is happening on this line of sight. So due to high gamma factors, we observe emission in some sense focused towards us. However, the situation can be more complicated, and different kind of scenario related to shocks and synchrotron masers have been recently discussed by Hangulian and his co-authors. In this case, the emission is anisotropic, so the picture might not be just one-dimensional, and potentially it provides an additional degree of freedom which can help to explain some characteristics observed in fast radio bursts. The second class of models is related to magnetospheric processes. And initially, these models were discussed in a different framework, not in the framework where the magnetic energy of a magnetar is released, but in the model which can be called radio pulsars on steroids. Thus, modifications of different proposed radio pulsar emission mechanism were discussed in these models. However, later on, it was realized that rotational energy losses are not sufficient to explain properties of fast radio bursts. So presently, I would say all competitive magnetospheric models are related on the magnetic energy release. And there are plenty of them. They involve different physics. In the center, there is a picture from a paper by Lu and collaborators. And in this type of scenarios, more or less standard picture is developed. But the authors try to fit it to the situation different from normal radio pulsar emission, so to fit better properties of FRBs. However, there are quite different models which should not work in the case of normal radio pulsars. Just to give two examples, on the left you see a plot from a paper by Maxim Lutikov, who proposed a model of free electron laser. So the idea is that in the magnetosphere, we have relativistic flows of particles, and due to instabilities in the magnetosphere due to reconnection, it's possible to obtain quite a complicated picture of the magnetic field, which is similar to the situation realized in free electron lasers. And so bunches of particles can oscillate in this complicated magnetic field, and they start to emit coherently, and this model can successfully explain many properties of FRBs. On the right, there is quite a different model, again by Yuri Lubarsky, in which an ejector is interacting with the current sheet surrounding the neutron star. So the emission is produced behind the light cylinder. And again, this model have many features which look reasonable to explain properties of FRBs. However, what are observations which can probe these models, because up to now we are not sure even what type of scenario is the correct one, or maybe both are correct, just we are dealing with sources of different types. In my opinion, the most discussed option to distinguish between two models is related to polarization measurements, in particular to burst-to-burst variability in polarization. And for example, in this case, it is observed that the polarization angle is significantly evolved from burst to burst. And this is not the situation which is expected in the case of the relativistic shock model, because in most of these models, as I said, you have a quasi one-dimensional picture. You observe the same patch of the surrounding media, and thus it's more natural to expect that the polarization angle is not evolving. And this is the case for many repeaters, but not for all of them. And the situation is tricky. So again, it looks like two mechanisms are working. Then there is a nice result related to periodicity in the burst structure, and the period is about 0.2 seconds. It's very tempting to say that this is the spin period of a neutron star. In principle, this result, if it is really a spin period, is much easier explained in magnetospheric models. It's much more difficult to obtain that picture in the case of relativistic shocks. So this is a point for magnetospheric models. Then it's known that fast radio bursts have relatively narrow radio spectra. And on the right, there is an extreme example of a very narrow spectra observed in one event. And in general, despite many attempts to detect simultaneously fast radio bursts at significantly different radio frequencies, it was not done yet. And it is better explained in the relativistic shock models because they can easier provide very narrow spectra. This is just another example of a narrow spectra of the first repeater. Then bursts have very complicated structure, and they show frequency drift. This is not necessarily related to the emission mechanism. This can be explained by propagation effects. Still, a successful mechanism might try to bring all these features in the picture. And up to now, it's well, there are different possibilities to explain these features. For example, it can be radius to frequency mapping in the case of magnetospheric mechanisms. It nicely explains many features of this frequency drift. However, it predicts some correlations which are not observed in fast radio bursts. Relativistic shock mechanism also can explain this frequency drift, and it was discussed in details in a paper by Metzger and his co-authors quite recently.
Sergey, you have 5 minutes.
Yeah, thank you. Then for several bursts, there are rapid variations, and we heard talk by Snelders on microsecond events. And also there is variability on the time scale down to 50 nanoseconds. And this is much easier explained in the magnetospheric mechanism, because in this mechanism, all time scales are typically much shorter than in the case of the relativistic shock mechanism. Then we come to the galactic event, to the famous bursts observed simultaneously in radio and X-rays from the galactic magnetar. And it is important that this high energy burst was quite peculiar. So it is different from many other bursts observed from the source, which were not accompanied by radio flare. And presumably it can be considered as an argument in favor of magnetospheric models, because then everything happens more or less in the same place in the magnetosphere. And if there are significant, strong correlations between properties of the high energy burst and radio burst, then it's much easier explained in magnetospheric models. Finally, we come to the question if repeaters and non-repeaters are from the same population. The answer is not known yet. And also probably there are other populations, and there was a recent paper by Crawford in which they showed 4 bursts with quite long duration and very large dispersion measure. Probably they can form an additional population with durations about 100 milliseconds and maybe longer. But I would say that these 2 distributions shown on the left significantly overlap, and it would be quite strange if repeaters and non-repeaters are explained by different emission mechanisms. And maybe the division line is not between repeaters and non-repeaters, but the situation is more complicated. What can be this division? In the case of relativistic shocks, the external medium is quite important. And now we know that fast radio bursts are observed in galaxies of very different types, including the one in the globular cluster. And so we can expect that media around neutron stars in all these cases, in star formation regions, in dwarf galaxies like in the first repeater, and with in the case of sources in, say, normal galaxies, and finally in the case of the globular cluster, then I would say that it can be a problem for the relativistic shock model, because bursts observed in these quite different surroundings look more or less similar to each other. At least we do not see a clear correlation. Maybe that's just because of poor statistics, and so we probably need to look more carefully at sources observed in different environments. That can be the way to distinguish between the two mechanisms. So I'm coming to my final slide. So conclusions and hopes. We think that magnetars are the sources. Again, small contributions from other types of sources are possible. And recently there was a paper by Most and Filipov in which they, on the higher level of discussion, demonstrated how fast radio bursts can be produced in coalescence of neutron stars, even with normal magnetic field. Still, magnetars might explain the main population of fast radio bursts. There are two frameworks, magnetospheric processes and relativistic shocks, and both of these frameworks are successfully developed and many models are proposed. They can explain main observed features. Both have some problems and both cannot be falsified yet. What about hopes? We need more counterparts in different wavelengths. Just in the discussion, there was a nice talk by Megias about the possibility to find optical transients with LSST. Of course, we need the definite discovery of spin periodicity, and we need more galactic events. Because for galactic events, it might be easier to measure delay between hard and radio emission. And I think that one killer of relativistic shock model can be if it is discovered that the radio pulse comes earlier than the hard energy pulse. That would completely close, in my opinion, relativistic shock models, and so the magnetospheric models would win. And of course, we need more data on events from sources of presumably different origin, because they are expected to be found in different environment. And again, it can probe predictions by models related to relativistic shocks. If all sources more or less look the same, then this might be magnetospheric explanation, because magnetospheres might be more similar to each other than properties of the surrounding medium. Thank you very much.
Thank you very much, Sergey. I'll say anyone who in the room wants to ask a question, please approach the mic, but we have some questions on Slack. The first is from Kelly Gourjay, who asks about the magnetar shock model. They say, would you in theory always expect a persistent radio counterpart, like a magnetar wind nebula, even if we can't detect it with radio telescopes? And if so, what kind of luminosities would we need to probe?
Well, in the case of relativistic shock models, probably always there might be a persistent radio source, but luminosities can be rather low. So in the case of magnetars with insufficient rotational energy losses, it can be difficult to power a strong radio source. Also, there was a question from Zorawar in Slack. Well, not a question, a comment. Indeed, in the paper by Sandra Merighetti in 2020, there is a claim that the radio signal came earlier than the X-ray signal, but in my opinion, despite the fact that, yes, this result deserves attention, we need better confirmation if this is really the case. But for example, Maxim Lutikov in his models used this argument, saying that only the magnetospheric model can explain this feature. But still, I believe that we need better data about possible delays.
Okay, we have some questions in the room. Go ahead.
Thanks for the nice overview, Sergey. A few days ago, Crawford et al. Put out a paper, discovery paper of 4 new Parkes 70 centimeter archive bursts from the early 90s, which were all more than like 150 milliseconds long or something. Such long duration bursts can naturally be explained with the the faraway shock models with different density gradients, for example. So I was wondering if you have any comments on how this can be reconciled with small-scale magnetospheric scenarios, and if it's even possible.
Well, that's a difficult question, and that's why in the beginning I mentioned that maybe there is the third population, and where is this slide? Okay, yeah, we can plot the third population far on the right on such a plot. And yes, maybe that can be a problem for magnetospheric models. But on the other hand, I cannot answer immediately because in principle, people just didn't try to explain such events. If we have to wait, in my opinion. Maybe there is a possibility to explain, but long events can be a problem for magnetospheric model in principle.
Yeah, thank you.
Okay, and we got last question from Ziggy.
Thanks for the nice overview, Sergey. I was wondering, on the topic of bandwidths, if I understand you correctly, you were saying that there's no problem explaining a range of bandwidths with the same emission mechanism. Does that break down if we really find that one-off events span multiple gigahertz of frequencies?
Well, this would be a problem for relativistic shock models. So up to now, the data can be explained with the relativistic shock models, but if you see something from 100 megahertz to 10 gigahertz, then for relativistic shocks, that might be a problem.
Okay, thank you.
Okay, thanks. I think we're going to need to move to the next speaker. Let's thank Sergey again. So the next speaker is Dee Lee, who's going to tell us about an evolutionary picture of FRBs. Do we have Dee on remotely?
Yes, I'm here.
Okay, you have 10 minutes, Dee. I'll tell you after 8.
Okay. Great. So I'll be quick. Can you see my full screen?
Yes.
All right. So I will. This is the title, and I'll mainly talk about results from the FAST telescope. So I frequently check this very useful site, the theory wiki. I think we have more than 50 categories of theories ranging from black holes to aliens. So I think it's still fair to say we are still some distance away from a conclusive origin story. I think there are actually 3 aspects of this effort. There's the discovery, there's the origin, and there's the sort of physics behind it, the principle. And most of the models so far, I think, can well explain the energy. But I think we are facing, once we get into how to actually produce the radio waves, we get into the more sort of complex physics in the, either in the magnetosphere or in relativistic plasma. And since we still don't understand the coherent length in pulsars, so I'm not that optimistic of achieving the sort of physical understanding of FRBs anytime soon. But certainly the progress of this field in terms of discovery and guiding to a astronomical origin, I think will happen in the next 2 to 3 years. So it's always quite a sort of a special experience going back to the 2 original papers. The first one by Duncan. There's that insightful sentence at the end, say hundreds of similar events could occur every day. At the time, it sounds a little bit optimistic, with just one detection. And the second paper led by Thornton, the last sentence says this FRB thing could help determine the baryonic content of the universe. So that has been certainly borne out by the McCourt relation. So I think in terms of discovery, this is quickly moving field. So our telescope is big. We change the 500-meter spherical surface in real time into a part of it into a 300-meter radii parabola. So some places of the dish is higher, some places of the dish is lower. So this sounds simple, but it does involve hundreds of thousands of fibers and moving like a 30-ton receiver dome. But all this has been demonstrated to work. And we also developed a slew of technology. The key one is the high cadence Cal injection, which facilitate the unprecedented commensal survey of pulsars, H1 imaging, H1 galaxies, and fast radio bursts. So the designed commensal radio astronomy fast survey, CRAFT. So I apologize that it's very similar to CRAFT, but we did put a survey to the end that will do the H1 pulsar and FRBs simultaneously in drift scan mode. So in about 2 years, we have discovered 4 FRBs, and this in relation to about 600 other detections published so far that tend to be dimmer, so presumably more distant, with larger dispersion measured. So it's small, but it does occupy this important parameter space. And we can easily extrapolate that into a lower limit to the FRB sky event rate at more than 100,000 a day. And there's no physical reason to believe that weaker FRB do not exist. So I think once we get into the SK era, we will be looking at an event rate somewhere between 1 million to 10 million per day. So regardless of whether we can understand the physical origin of FRBs, it will remain an important branch of astronomy for decades to come. And Dr. Chen-Hui Lu, when he looked at the drift scan data from 2019, May 20th, he noticed repeated bursts from this one location with a dispersion measure around 1200. So this gets to be exciting. And next year in July, collaborated with a team led by Casey Law, we managed to localize it with VLA real fast. And almost within 24 hours, we were able to get the first redshift measurement from Palomar. And we later follow up with CAC, CFHT, Subaru, and also other major instruments. So this is a press image from NRAO. So you can see that blinking light represents the position of the FRB. It is on the peripheral of a Meadow-Proa dwarf galaxy. The redshift measurement from both CAC and Palomar are consistent with each other. And the measured redshift is much lower than the estimated DM redshift. So 1200 taking off the galactic and the local galaxy host ISM contribution is roughly redshift of 1. The measured redshift is only 0.24. And it also has a confirmed persistent radio source counterpart within about 100 parsec of the burst. So this is only the second such source. So this is a blow up of the optical and the infrared images. So here's the location of the burst. And we still don't have a higher resolution optical image, but it looked very similar to the irregular dwarf on the right, which is about 7 kiloparsec across and 40 times closer. So it's roughly the same physical size, and there's a chain of giant H2 regions on the upper north, and this is suggestive of a relation between sort of a recent star formation and repeating FRBs. So this is a summary of the discovery paper. It has the highest confirmed DM from the host. It's the second compact persistent radio source counterpart and extremely active. So it's active in a different way in that every time we train our telescope on 190520, it produces bursts. So it doesn't have as high a peak burst rate as some of the other repeaters, but it's very reliable. And it also is deviate severely from the McCord relation. So I will later come back to this point.
You have 2 minutes.
All right. Okay. So so we also after the discovery of 190520, we also have managed to catch an extremely active episode of 121102, and which recorded more than 1600 bursts and get this bimodal energy distribution. It has a lower part of the energy is the log normal, which usually represent a stochastic process. On the higher energy end, it can be well fit by a Cauchy function, which can be produced by the ratio between two independent random processes. So there are some models. One of the model does produce this bimodal distribution from Magnetars, so that from Yuanpei Yang and Bing Zhang. However, it does present some more difficulty for a single isolated Magnetar, since we practically rule out any periodicity or even quasi-periodicity between 1 millisecond and 500 seconds with such a large and good cadence of sampling. And also the total energy release during that 2 months corresponds to about 40% of the full available magnetic energy from a Magnetar. So there's some challenges there. So with such active sources, we start to look for polarization, but to our initial dismay, we just cannot measure any RM from 121102 nor from 190520, and we know that they should exist. So we finally settled down on this multipath propagation picture, and this is a monitoring campaign led by Yifeng, my former PhD student, now a full staff in Zhejiang lab. So this is the result in combination of results from FAST, GBT, SCAP, CHIME, VLA, and LOFAR. And you can see that there's a systematic depolarization from high frequency to low frequency. At high frequency, you tend to go to 100% linear polarized. And at the characteristic frequency, just the percentage of polarization just drop like a stone, and it can be well fitted for every source with this single parameter, which is the sigma Rm. Sigma Rm represent the local variation of the electron density times the magnetic field. And also, I think it's by no coincidence that 190520 has the highest sigma Rm and 121102 has the second highest. And these two are the only two with a confirmed persistent radio source counterpart. And this could well represent a younger stage of a repeater evolution. So there's a more detailed paper from Yuanpei Yang and also a slew of other paper from Stellar, Casey, and Nino-san. And also we are seeing the initial evidence of reversal magnetic field around this repeater. So there's two papers currently under review. So one interesting fact is the scattering width in time that correlates very well with the sigma RM measurement. I think that's support that there is a dense plasma surrounding the source, so they basically come from the same plasma screen. This is just a sort of advertisement. So there are 4 papers currently under review for this even more extremely active episode from 2020, 11/24. So in 4 days, there are more than 700 bursts with a peak event rate at more than 500 per hour. And it's present a very complex structure, and still we don't see any periodicity nor quasi-periodicity. So I think the question is still out there, how we can produce from a faster spinning compact object. So here is my ending, and it's very hypothetical. So I think at least a significant kind of fraction of the FRB may follow this evolutionary track from repeating to non-repeating. So that's a drop in burst rate. And its surrounding plasma will disperse. So the DM host will eventually drop to 0. And it will go from higher sigma RM to lower sigma RM to unmeasurable sigma RM. That's just the dispersion of the electron and a stabilization of the magnetic field. And at initial stage, it could have the persistent radio source, then it will become fainter. Just picture a supernova remnant. And the RM could be more complex because there could still be a black hole or some other object in the neighborhood. So that's all. Thank you.
Thank you. Thank you for that. I think we have a time for one question, and we have a few coming in on Slack. The first is from Zhilai Zhang, who says your 4 FRBs that you presented are not very bright. I'm just wondering why you haven't detected any brighter ones. So wondering about how much observations you've done over the 2 years.
Right. So yeah, so our detection rate is fairly low. It's 400 hours per discovery, and so I think the reason they are faint is just that it's in certain beam when you basically have larger volume and more galaxies at larger distances. So I think it's still consistent with just a simple probability expectation.
Okay, thank you. Well, with that, let's thank Delia again. Next, we have Navin Sridhar, who's going to tell us about ULX bubbles.
No. It works. Thank you. So yeah, I'll be talking about some applications of hyperaccreting X-ray binaries to FRB persistent radio sources and stellar merger radio transients. Okay, I'll just skip these slides. Thanks to Sergey and everyone. Yes, Magnetars can and they do generate FRBs. However, there are some challenges that Magnetars face in order to explain all the features of FRBs, including, for example, the long periodicities, like hundreds of days. Look out for Zorawar's talk for some ideas. And further, we have Chime has reported these exciting spectrotemporal dichotomy between one-off and repeater bursts, which is suggestive of multiple engines of FRBs. And as you can see, this is a repeater and non-repeater. And if you check out this paper for a toy model that for explaining this dichotomy. Also, yeah, so this is a very famous slide. We know that FRB2022 was produced like 250 parsec away from its nearest star-forming region, which is not really a conducive environment for a young, few tens of years old magnetar to be there. And also, FRB2020E was also detected in a globular cluster, again, not a place where you can find young magnetars. These are suggestive of older population, typical of X-ray binaries, for example. And we developed a model for an accreting engine for producing FRB-like emissions. And the repetition here would be due to the episodic flares or reconnection plasmoids that are launched from the base of the jet. And the periodicity here would be explained by the precision of the jet along the axis of the observer. I should emphasize here that the FRB here is produced at AU scale, so there is no issue with dispersion measures, and also this can also explain some of the microstructures in FRB, because the mergers of plasmoids can produce giant pulse nanoshot-like features. So it is consistent, in fact. So this model also very nicely explained the chromatic properties that were observed from 1809-16, that the high frequency bursts arrived earlier than the low frequency ones within an active phase window. We explained that using the synchrotron maser scenario, and that the structured nature of the jet also naturally explained the emission frequencies, the arrival time of bursts at different frequency at different times for different frequencies, and also it explains the burst width, that being shorter for high frequency ones and narrower for lower frequency ones. It also explains the DM constraints. This is just a background, and now comes the real part, the latest one. We have observed persistent radio counterparts to FRBs, 121102 and 190520, and these are compact parsec scales, optically thin synchrotron with luminosity of 1039 erg per second. These are too luminous in the radio band to be supernova remnants, and more luminous than local star formation activity and less luminous than a typical GRB afterglow, and they exhibit extremely large rotation measures, or rather the FRBs that travel through them, they carry a large rotation measures. And this requires the immediate surroundings to be baryon loaded, because just leptonic or paired plasma cannot really impart this large rotation measure. So we do know that some X-ray binaries, they are surrounded by wind-inflated bubbles. So these are examples from two sources. This is the Manatee Nebula from SS433, because it resembles like a manatee. So we do know that they inflate these bubbles. So the model that we have developed here is we put in these hyper-accreting sources, and we think that these bubbles are inflated by the accretion disk winds and the jets when they interact with the circumstellar medium. And this is the inflated picture. So you have the central engine. The FRB could be emitted from along the jet axis. As it passes through the nebula, it imparts some rotation measure to it. And the persistent radio source could be produced from the nebula that is inflated by the jet and the accretion disk winds. These contours, they are the different shocks that are caused due to the interaction of these winds with the CSM, contact discontinuity, and the shock winds. And yeah, we call them hyper nebulae because these are comparatively short, like 1 parsec in size, and these are much more luminous than typical ULX binaries, ULX nebulae. What we do is we've evolved the particle energy and field energy distributions given various cooling losses. And this is how various properties of the nebula evolve. For example, the number of particles increases up until a point when it's active, and then it stops increasing. T free here is the free expansion timescale, after which the nebula starts entering the Sedov-Taylor like self-similar expansion phase. And this is how the magnetic field strength evolves, which we can calculate using this equation, and how the nebula evolves. And this is how the expansion velocity of the nebula evolves, and this is the nebula radius. As you can see, the nebula radius is
0.1 to 1 parsec for different models. And what we do is we also evolve the injected particle distribution self-consistently, accounting for all cooling losses, all radiative, adiabatic, Bremsstrahlung, inverse content, synchrotron, as well as expansion losses. Yeah, once you perform this, at each and every moment in time, you have a different particle distribution with which you can calculate what the emission will be from this nebula at different times of its evolution. And that's what we do here. The top panel here, it shows the spectral evolution for at 1 year, 100 years, and 10,000 years of the nebular evolution for typical parameters of companion star's mass of the black hole that's accreting, or it can even be a neutron star, that's okay, and the accretion rate, the particle density, the wind velocity, the jet velocity, the magnetization, and so on. The bottom panels, they are the simulated light curves of this nebula at different frequencies. This shows that at millimeter wavelengths, this seems to be the highest, but the detection probability is largest. The chance of detection are largest in radio, of course. CMB surveys may not really be able to detect them, but maybe targeted ALMA searches can help.
You have 2 minutes, Navin.
Yeah. With this, we can also, so now that we have the particle distribution self-consistently calculated, we can also calculate what the rotation measure will be at different times, and the dispersion measures, and the local dispersion measure at different times. That's what we do here for different models. Note that the RM can start increasing again. While you only see a decreasing RM, it can also start decreasing again for certain cases where the active timescale of the nebula is much larger than the free expansion timescale of the nebula. And the characteristic timescale for the fluctuations in RM can also be calculated. And this is just given by the shock dynamical timescale, which corresponds to the eddy turnover timescales in the turbulent downstream medium of the shock nebula. And this is also very well consistent with recent estimates of RM fluctuations from McKinnon et al. And Reshma Thomas from different sources. I'll quickly skip this slide. The previous slide just shows how the spectral index and other properties vary for different accretion rates. Finally, I produced a bunch of these synchrotron light curves, spectra, and what you see here are the spectra for FRB 190520 and 121102's persistent radio source. Here, for the first time, we fit them by producing these self-consistently evolved models by taking a weighted average of these spectra. This is a generalization in that sense that it's not just a one-zone simplistic model. We generalize it to electrons injected into the nebula that we let them evolve independently. And here you go. This is the spectrum. And for some model parameters, of course, I can talk about it more if there's interest. And here's how the RM varies for 1905-20, 121102, and it very well explains the RM evolution also. So yeah, RM, this fit models reproduces the RM evolution of observed from FRBs really well, and constrains the ages to be around 10 years old. And 1905-20 seems to be a younger brother of 121102. Yeah, I'll stop here and happy to take any questions.
Thank you for that. You say that was 10 years old?
Approximately. It's young. That's all you have to take it from it.
Okay. Yes, go ahead.
Yeah, thanks for that wonderful talk. Your last slide, I was just seeing the results of the modeling. So do you have what is expected from these for the FRB2022 and the second one, like in terms of the mass loss rates I know it's here, but it's kind of complicated. Can you like let me know?
Sorry, can you rephrase your question?
Yeah, so what's the consistent mass loss rate and maybe ejector velocity as well for FRB2022, like as the model predicts?
Got it. Okay. So for example, for FRB2022, the mass loss rate would be 10 to the 4 to 10 to the 5 times Eddington.
So like what's the meaning for, like, what are you implying by that? What does the model imply by that result?
If you want in terms of luminosity, that would be like 10 to the 41 erg per second would come out in the form of accretion disk winds, and that is what is required in order to pump enough baryons into the environment in order to produce the seen local dispersion measure, the rotation measure. That's such a large rotation measure. It's the way it drops, and also the luminosity of the seen persistent radio source. It cannot be much smaller. And I would also like to emphasize here that this accretion disk wind luminosity is consistent with what accretion power you need in order to produce an FRB that is as luminous as 12102 from the jets.
Thank you.
Yeah.
Thanks, Navin. Oh yeah, we'll do one more question, yeah.
I think it's quick. You might have said this and I missed it, but how do the ultra luminous X-ray binary or these system rates compare to that of FRBs?
How are these?
How do the rates compare? Like how
Oh.
many compared to what we're predicting for FRBs? Maybe you said
Yeah, we actually have more such sources than FRBs. So we are in a good problem regime. It's fine if just like 1% of them are FRB producers. And I'm not really going to argue that these are the sources of FRBs. Some FRBs can be produced from them. But the main point being these hypernebulae, they exist. These hypernebulae, they exist in our universe a lot, and regardless of whether they can explain, they can produce FRBs. They do produce FRBs. They presage energetic transient from common envelope like mergers, and they can be signposts for future LIGO merger events, and they should be continuously observed, and targeted follow-up should be performed with VLBI based on VLAS-like surveys. This has stellar binary evolution implications too.
Okay, well, let's thank Navin once more. Next up, we have a remote talk from Mayuresh Surnis. Do we have? Who's hopefully online?
Yeah, I'm here.
Okay. Okay,
Should
take
I
it
share
away.
my screen?
Yes.
Okay, right. Can you see my screen?
Yeah, looks good.
Okay, great. Hi, everyone. My name is Mayuresh. I'm currently working as a postdoc at the Jodrell Bank Center for Astrophysics in the METRAP group. And today I will be talking about slowly rotating neutron stars as potential counterparts to some FRBs. I initially wanted to talk only about repeating FRBs, but there are some recent results which sort of makes it a point to not talk only about repeating FRBs. So just quickly summarizing the FRB landscape, it's rapidly evolving with multiple repeaters, host galaxies, dedicated follow-up observations. There are many observatories that are producing a lot of observational inputs through projects like the CHIME FRB, the CRAFT, and the CRAFTS survey at FAST. And then, of course, METRAP, and I'll be talking about a few results from METRAP in my talk. And it seems like there's this clear emergence of two or perhaps maybe more subpopulations occupying different positions in the phase space. Here's one example from the CHIME burst, where the one-off events, as we all know now, have a larger bandwidth, smaller duration compared to the repeater bursts that are smaller bandwidth, and they are slightly longer in duration. So just a template slide for an example of what typically single one-off and repeating FRBs look like. The one on the left is from Meerkat from a paper which was just recently submitted by Fabian. As you can see that it's just a single Gaussian-like pulse, which almost occupies the full frequency range compared with the 121102 bursts observed with the Meerkat, wherein they show a lot of frequency structures, drifts, the sad trombone effect, and so on and so forth. Then recently we have also seen that repeating FRBs show periodicities, like the 121102 showing us 157-day periodicity, and then the Chime FRB showing a 16-day periodicity. And thankfully, I would not have to go through the models because the speakers before me have explained quite a lot how magnetar flares have often been invoked as potential central engines. There have also been binary orbits and precessing neutron stars that have been invoked to explain the periodicities in repeating FRBs. However, I would like to now concentrate on a few properties of both repeating and one-off FRBs, which is why I said some FRBs, not just repeating. Marcus already showed this plot from XT1810. This is from our UGMRT campaign, which we started in 2018 to observe J1810. And especially these pulses in the last column, the right column. And just for comparison, I've put in two recent Chime FRBs that are one-off FRBs, but they show multiple quasi-periodic pulses. And I'm sorry for the resolution, but it seems that the timescales also are pretty much similar, tens of milliseconds, with a few millisecond gaps in between. So there's already sort of an observational similarity between how the pulses look like and even the time scales. Then I will also, the second possible slowly rotating neutron star counterpart is the so-called ultra-long period neutron stars. As you all might be aware about Manisha's paper on the 76-second magnetar, which we discovered with MeerTrap. And this is a collage of the sort of template pulses types that this pulsar emits. And you can clearly see that there are a couple of pulse types, especially the double peak type or the spiky type, which doesn't really cover as much the frequency range, as well as it also has multiple components and quasi-periodic structures. And on the right, it's just another FRB with the 216 millisecond periodicity, which was reported from Chime recently. And to make the comparison more specific, here's an example of a few of the quasi-periodic pulses showing very, very different timescales over which you see periodic structures, and they range from almost 30 milliseconds to about 150 milliseconds. The point that I'm trying to note here is that although the periodicities, the quasi-periodicities are of the order of a few milliseconds, we know for sure for this pulsar at least that the rotation period is much, much longer. So you might see quasi-periodic pulses, but it may or may not always represent the true periodicity of the central engine. It might still be a binary, or it might still be a slowly rotating neutron star. Then comes another example of an ultra-long period neutron star, which is the gleam source. So here on the left, I have shown the dynamic spectrum, which is the dispersed and the de-dispersed. And you can clearly see sort of the sad trombone effect here. And I've just shown some pulses from 121102 just for comparison to show that there are structures that are similar in this pulse, as well as some of the pulses that are seen from 121102. In the middle, I have showed some pulse profiles in time, and there is another FRB which was recently discovered. And you can sort of clearly see that although in this case the timescales are slightly different, but the structures are pretty similar. And there is this pattern that is emerging that the frequency structures are similar. In some cases with magnetars, the timescales are almost identical, whereas with the ultra-long period neutron stars, the timescales are slightly different, but morphological similarities are pretty much there. Now, let me move on to another source which was discovered with MeerTrap recently. We are calling it an extremely transient radio emitting neutron star because, as the name suggests, we detected this through single pulses using the MeTrap backend. And because it was observed in a simultaneous observation with mean time, we detected about 100 pulses from this source. We were able to actually calculate a period of about roughly 10 seconds, which puts it in the potential magnetar range of periods. Why I'm seeing it's a potential magnetar is the interesting bit about this source, because it was detected only in a single observation, which spanned 20 minutes. And to date, I think there have been about 63 epochs of observations of this field, and it's spread over more than 3 years. But it has not been detected in any other epoch whatsoever. And as far as we know, we tried looking at radio images from other telescopes, other frequencies, other times, and we haven't seen any detections at all. The flux density, if you calculate from the image, and if you just take an RMS of the lowest RMS of the image that we have, the flux density ratio seems to be something of the order of 130. So it's pretty bright, and it was pretty bright for a very short duration of time. It sort of has two peaks in the pulse profile, and the second pulse profile again shows these very, very well-known structures in the pulse, and you can see that the pulse duration is about a second and a half at the most, and you can see all these quasi-periodic structures. This is just one pulse from this. I think of the 100-odd pulses, we see different patterns, which is something similar to what we saw in the in Pulsar 0901, and we are currently working on this paper, which will sort of hopefully come out soon. So in summary, what I would like to point out is that we know that repeating and one-off FRBs show very different structures in time and frequency, but there are some recent results which have sort of started showing similar properties. Then radial out magnetars like XT1810, they show pulse microstructure similar to some one-off FRBs, the ultra-long period rotating neutron stars, the 0901 and the Gleam source. They show properties that are similar to both one-off as well as repeating FRBs. And the recently discovered extremely intermittent radio-emitting neutron star, it also shows the pulse microstructure reminiscent of the one-off FRBs. And what I would like to end with is the potential in commensal real-time surveys like the MeTrap, because they are uncovering a wealth of these ultra-long period neutron stars that may help bridge the gap between the galactic magnetars and the FRBs. So yeah, I think that's where I would like to stop.
Thank you.
Thanks.
Have we got questions from Irish? I don't see it on the Slack. The extremely intermittent transient neutron star. Can you remind me the timescales of it? Like.
So we saw it in a single observation which lasted about 20 minutes, and it's been observed for about 63 times, which is spread over almost 3 years now.
Well, what's the total TOBS?
So the on-field time is about 11 hours.
Okay, all right, thank you.
Yeah.
Oh, we have a question from.
I have a question.
Oh yeah, go ahead, Casey. Yeah.
So the new discovery is found in the same method as the other slow magnetar. Is that the right? What I'm hearing here. There's two examples with the same technique of image plane discovery, and so. Sorry, I guess that's a statement. Manisha is saying yes.
Yeah, so we discovered it through the transient pulse detection. It's because we had imaging data simultaneously that we could do the localization through interferometry.
I see.
Because we detected these pulses in the incoherent beam, not the coherent beam.
Okay, thanks. And I guess I was wondering if you had estimates of the density of the likelihood of discovery given the time on sky and so on? Are they consistent between the two populations?
I don't have the answer offhand, but we are trying to work it out. There's one other example I have, which is of the extremely intermittent pulsars. I forgot the J name, but there was this one pulsar which was sort of off for 2.5 years, and it was just detected in one off 20-minute observation. But I think apart from that, there are no known examples. And as I said, I don't have the answer offhand, but I can maybe get in touch later. And
yeah, thank you.
Yeah.
Okay.
Correction also that make sure that the GLEED source, that's ionospheric, not spectrum.
So I don't know if you heard that, but Mayuresh.
No, not
about the GLEEM-X source not being the sad trombone, but being rather ionospheric scintillation.
Okay.
Let's thank Mayuresh once more. And so the last talk in this session is by Zorawar Wadiasingh.
Okay.
Oh, you're ready. Go for it.
So this is well, since we're running a little late, I'll go quickly. So this is the radical proposition that the periods that we see are actually rotation periods. And so the motivation is, of course, we see these periods in FRBs, these activity windows that are periodic. And so people have talked about that, and there's three models, binary models. Binary models, precession models, and the rotation. Rotation is what I'll talk about. So let's just go through the challenges for the other models. So the precession models generally require pretty young sources. That's challenged by the localization here that says, okay, this is at least a few thousand years old for our three. And then for precession models, you should also detect sort of an underlying periodicity of say 1 to 10 seconds if it's a magnetar. So we don't see that, and that's been pretty well studied in FAST and other papers. And the precession, sort of the deformation depends on the toroidal magnetic field, and that decays with age. So you'd expect much longer periods in precession generally. The shrouded binary models, this has also been talked about, but the frequency evolution or activity window dependence is opposite what you expect from a shrouded scenario. The eclipse fraction should decrease with higher frequency, and the trailing leading ingress and egress behavior should be the opposite of what is observed here. The DM variations are also consistent with zero or pretty, well, depending on which instrument used, but they're pretty small. And if you look at other massive binaries like a B1259, the DM variations can be much larger. There's no low frequency spectral cutoff, and of course the other challenge is where's the underlying periodicity if this periodicity is an orbital period. So the other thing is that the source density of R3 in particular is quite low. So it's not a radical proposition to say, okay, we need something special here. And it sort of favors an exotic explanation, this sort of rarity of R3, for example. So there's other selection effects here. So for example, in a low twist model where you have magnetar oscillations that are actually causing the FRB in some sense, basically instead of pulsar rotation, you have a magnetar that's oscillating, and that sort of explains the large energy scale difference between pulsars and pulsar radio emission and FRBs. So the magnetar oscillations have a spectrum, like earthquakes have a Gutenberg-Richter law. And there's a threshold where the charge density plays a role. And so if you exceed that threshold for the amplitude of oscillations, you can get an FRB. And this charge density is basically the Goldreich-Julian charge density. So if you have a long period magnetar, the charge density is so low that you're far more susceptible to these instabilities. And you can make these toy model luminosity functions for For example, this one is just for one oscillation mode, and so we can add more parameters and describe a luminosity function. So people have already talked about some of the candidates. This is another candidate. This object here is a so-called CCO. It's 6.7 hours. It has millisecond short duration X-ray bursts like magnetars. It has outbursts. It has a non-thermal hard X-ray pulse tail. And the proper motion here from Chandra suggests that a wide binary would have been disrupted. So this is a strong candidate, and it's 6.7 hours is the period. It's a radio quiet, though, so it's not well known in the radio community, but it's well known in the X-ray community. Then there's the galactic burper. This is a 77-minute source that was discovered about 2 decades ago. And if you believe the distance and the variability, then it's clearly a coherent source, although its nature is still quite uncertain. We never know what it is because it came on and went away. Then there's the Gleam object. Again, it's a coherent radio source, and I don't have time to show this, but a white dwarf can be largely ruled out. It also can't be a rotation-powered pulsar, or it can be, but then you'd require an extraordinarily large magnetic field. That's sort of absurd. So it's probably one of these ultra-long period magnetars, and its period is about 20 minutes. Then there's the mirror trap source, the MTP-013 or PSRJ-0901. It has a P dot, and the really interesting aspect here that it's only 300 parsecs away. And this is what a large part of the talk will go into. The other interesting aspect here is that it has these harmonically spaced QPOs, and these are consistent with crustal modes. You expect this sort of 10 millisecond or 100 millisecond time scale to be the crustal modes, and sort of inconsistent with alphenic modes, especially since it's the radio emission is polar cap radio emission, and you have to connect to the light cylinder. So the mechanism, so there's lots of mechanisms. I don't think I'll have time to go into this, but phenomenologically, magnetars have shown these P dot changes, these spin up, spin down changes, and so-called anti-glitches. And there's plenty of them, and just phenomenologically, if you have a large number of them, you can increase the period exponentially. One way to do this is these charged particle winds. You basically have a wind magnetar activity that blows open field lines. You go from a dipolar solution to a monopolar solution, breaking index from 3 to 1. Basically, your period increases exponentially with this characteristic time scale here that depends on the strength of the wind. I should also point out that we know that phenomenologically the breaking index of magnetars is less than 3. So for example, Tendulkar showed that for a share, I think it was 1806, so the kinematic age constraint really implies that the breaking index is less than 3. So we know these sort of episodic winds are going on in magnetars. So we did a toy simulation in this paper, and what you get out of this sort of population synthesis of magnetars or evolving magnetars in the PP dot diagram is you get a big bump at the usual period of about 1 to 10 seconds, and then get this long tail at the 10 to the minus 3 or 10 to the minus 4 level of magnetars with extraordinarily long periods. And this is showing the sort of density plot in PP. The other possible mechanism is fallback accretion. For example, the RCW103 central compact object. The supernova from Chandra studies, the spectroscopic studies show that the supernova is sort of weak. And so you could have a fallback episode. And when that happens, you again connect the field lines to the disk and open up field lines and enhance your spin down that way. And this evolution of being exponential is a power law. And this depends on the details of the disk structure and if it's a thin disk or thick disk and other aspects. So the implications. So I guess since I'm running out of time, so the GleamX and the MTP source really imply that there's a lot of these objects and they're old. And that implies that the magnetic field of magnetars don't decay, or at least some magnetars don't decay as fast as we thought. And that's extraordinary in the sense that there's a lot of these highly magnetized, slowly rotating neutron stars out there. So let's go into the source density estimates. So we did this Monte Carlo using this method, I guess Vicky did a long time ago, where we birth sources in the galactic plane, we propagate them in the galactic potential with kick velocity distribution, and we get sort of a minimum age here for the gleam source and for the MTP source, because their formation channel cannot exceed the core collapse supernova rate. So this is a strictly lower age limit in some sense. So it implies at least 10 to the 3 gleam-like objects in our galaxy, and 10 to the few times 10 to the 4, or even more, this MTP, PSR 0901 type objects. So there's also constraints from magnetothermal evolution or cooling, and this gives you constraints on the age of lower bound on the gleam object and sort of a upper bound if you believe these models, but there's an uncertainty here of the mass and composition of the crust that gets these cooling curves for magnetars. So, so if you combine these age estimates, you get this sort of the RCW103, the gleam, the MTP, they all sort of lie on this formation, the birth rate of about 10 to the 5. So they're compatible being born in core collapse supernova and compatible being the significant portion of the core collapse supernova rate. So that's extraordinary. So there's a lot of them out there to be found. And this is just showing that, okay, but there's also possibly a trend that, as you expect, that the sort of the longer period objects are rarer in terms of source number density. And so the bottom line is these are old objects, and the rarity increases with period. So the main, so the takeaway is that the magnetar strength fields seem to survive for mega years, at least in these objects, and it has to be a common channel. It's a challenge for these standard magnetothermal evolution models. And it's not surprising that the magnetothermal evolution models are quite a difficult problem, and they're nonlinear and they're path dependent. So it's not surprising that you would find channels like this, but the bottom line is cannot be an uncommon track since there's so many of them. It's interesting prospect for the M81 globular cluster FRB if it's an old magnetar, a few mega years old. The evolutionary track of these systems is totally different from normal magnetars. So the general idea, I think, here is that it's a core field. The crust field has decayed, and what's happening here is there's a neutron-proton superfluidity in the core, and this suppresses ambipolar diffusion in the core. And this is this famous Goldreich-Resneger paper, or Glampadakis or Gabler, they all talk about this. So what happens here is the solenoidal field decays, and you're left with this poloidal core field. And so it's a sort of a low twist, almost purely dipolar configuration that's left over that has very little free energy other than to make FRBs and other transient phenomena. Okay.
Thank you. Thank you for that. And given the time, I'm going to allow one question, and there's one on Slack from Clancy, who says, you mentioned neutron star crustal modes. What kind of modes are they?
They're torsional modes or shear modes. It turns out those are the ones that couple to the magnetosphere the easiest. You could also have F modes, which are global oscillations. But the crustal modes are probably the ones that are going on here, and they have a frequency spectrum that starts at around 10 hertz and goes up from there.
Okay.
So kilohertz.
Okay, let's thank Zorawar once more. So there was a question about whether we would start the next session slightly late because we've ate into lunch a bit, and we can just start 5 minutes late. That's all they're giving us. But we'll do that. Okay, see you then.